its contents. Cool. Did anybody read chapter 3? Okay. There is something about arrays, yes. Did anybody not cover arrays in their previous Java class?
Does not taking a Java class.
That's a special case. We can chalk that up to a special case. Are you familiar with arrays?
Yes.
Okay. So the first section of chapter 3 is primarily just here's how arrays work, in case you forgot. A lot of the concepts are very similar to concepts with objects because of the references involved. And I think we talked a little bit about arrays on the very first day. Certainly about the stuff on page 111, the enhanced for loops for arrays. I call them a for each loop. Same thing. And I mentioned that, I think I mentioned something about iterating and iterator and iterable. I don't know why the book doesn't talk about it in this chapter. The book kind of mentions it and then goes on to talk about other things. So I'm going to skip ahead to the last section of this chapter, the Java hash set and iterators. I'm going to ignore the part about the hash set. You've, in theory, read about it. So you know vaguely what hash set is. The whole idea behind iterators is that going over a collection of objects and doing something to each one in turn is something that we do very, very frequently. And it would be really nice if Java just provided this way that we can do that. The for each loop is half of it, but in order to say that something is, for lack of a better word, for eachable, there needs to be some way of describing this object that means that we can pick out its component parts and do something to each one in turn. And this is accomplished through two what are called interfaces. Dion, in Visual Basic we talked about inheritance, right? Vaguely? Okay. Inheritance is a topic that's handled later on in the book. Again, I don't know why. And also it seems it's a topic that didn't get covered in most of your previous Java classes. The basic idea is that since a dog and a cat are an animal, why should we describe what an animal is and then describe the properties of an animal that a dog and a cat have on the individual dog and cat classes? So we define one animal class and then say a dog is an animal and a cat is an animal. And by virtue of being an animal, it has all of the animal things. Interfaces are similar to that, except they specify just the methods that a class can have. More accurately, the method headers, the method signatures. How the outside world can interact with a particular type of class. An iterator and iterable are two such interfaces. They basically say that this particular class has methods that allow you to iterate over it. And they're really very simple interfaces. They're probably the simplest interfaces in the Java framework. There are some interfaces that list many, like 30 different methods. So, two interfaces, iterable and iterator. Iterable indicates that this class can somehow be iterated over. It is iterable. And it means that your class implements one very specific method. That's the iterator method. It starts with a lowercase I. That method returns something that conforms to the iterator interface. Most of these mechanics are things you can ignore for the time being because we'll talk about them in more detail, but they are necessary to do the assignment. And I kind of take some shortcuts. I say, here, put this code in. Or take the sentence and turn it directly into code. One of the conventions in Java is that an object is its own iterator, so the iterator method simply returns this. This? Not so. I don't know, I've been writing Objective-C today. In Java it's this. So the iterator method just returns this, which conforms to the iterator interface because it implements two methods, hasNext and next. HasNext, it returns a Boolean whether or not there is a next thing, and next returns the next thing. The full documentation on this there we go. There we go. So here's Iterator, and it says it implements a hasNext and a next. That remove method, that's new, relatively new, and it doesn't specifically, it doesn't return anything, so it doesn't really have to do anything. In theory, it's supposed to remove something from the collection, but in your implementation, you can just stub it out. And as I said, the iterable interface, which has a single method, iterator. You can ignore this angle bracket stuff for now. We'll talk about that a week from today. That's something called generics. That's chapter 5. So, as an example of that, let's kind of start this bag of ints that the book uses as an example for this chapter. So int array bag. Guess we might want some actual Java syntax there. Public class int array bag. In order to say that this class conforms to these interfaces, we say implement iterator iterable. Did anyone's previous Java class talk about inheritance, interfaces, abstract classes, any of that stuff? Okay, so this should look familiar to you. If this doesn't look familiar to you, don't worry about it too much. Just, this is a piece of code that you will need to use in the assignment. And we'll talk more about exactly how it works much later on in the book. That is, if you're really anxious and can't wait, that's chapter 13. So the very end of the semester. So with that in mind, we know we have to implement 4 methods total now. We need to implement, from iterable, we need to implement an iterator method that returns an iterator. Iterator, yes. I'm going to stub the methods out first and then go back and implement them. We know we need to implement a method that returns a Boolean called hasNext. We know we need to implement a method that returns, this is an int array bag, so it should probably return an int. Called next. And what's the last one? Remove. Returns void. So this one we can leave stubbed out because it returns void. We don't actually have to return anything, which means we don't actually have to do anything. If you try to remove something from this int array bag, it might not make sense. But we can leave that like that, at least for now. We'll go back and implement it when we actually implement what the book talks about for this int array bag. Iterator, I said we should just return not self. This is not Objective-C, this is not Objective-C, this is not Objective-C. Return this. Now we need some way of figuring out what element is the so-called current element, so that the word next and the word hasNext is actually meaningful. So for now, we'll make a very simple implementation. We'll create an integer called current, which will point to the current thing that we're iterating over. hasNext, if it's beyond the number of things in this collection, it should return false. There are no more things. We've gone past the end of the collection. Since we don't actually have any objects in this collection, we'll just say it returns a sequence of integers from, let's say, 0 to 10. So if current, return current less than 10. So that'll give us 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. And since we don't actually have objects, we'll just return current. I guess I have to save this. Okay. In order to use this class, I should probably make a new class called public int array bag main. My Java syntax is not working well today. Did I spell everything right? Almost. So, assuming that my implementation of int array bag does what I said it will, what will this main method do? No ideas? What did I do wrong? We need an import. This is one of those issues between the version of Java that I have and the version of Java that you have. Yeah. Is that right? This is what they improved things in Java 7. So for now, the instructions in the assignment are slightly different from what I'm doing. Those instructions work with. Actually, those instructions, because they make use of generics, even though they don't say, "Hey, I'm making use of generics," they work with both Java 1.6 and 1.7. The way I'm doing it, because I'm running Java 6, I have to do it a slightly different way. And I didn't do something right, because I now have an infinite loop. That could help. Right, implement current, increment current after I evaluate it. That is correct, it does not. There we go. Okay. There we go, that's what I expected. So, in reality, if I were to use generics, like the assignment talks about, I could do something like this. That says this is an iterator over integers. Then I'd have to change this to integer, and that's mentioned in the documentation. That's what this E thing means. It basically means some object. This is an interface that represents an iterator over some object, and then everywhere that E appears in the documentation, you replace it with that type. So I put integer here, which is basically a wrapper type around the primitive type int. So next must return an E. Next must return an integer. That's the only change I have to make there. And I do have to say that it's an iterable over type integer as well. Which means that this doesn't just return an iterator, it returns an iterator over integers. So that's kind of a crash course in Java doesn't let you get away from using generics. Unfortunately, you can't ease into using generics. So that means that this iterator gives me integers, and when I compile and run this, it does the exact same thing. Questions? Is anyone totally confused? Is anyone partially confused? Okay, that is okay. Java has the irritating quality that there's no easy way in. You either use a bunch of stuff right up front and don't know what's going on, or you learn a lot of stuff and then can't really use it until you learn all of it. So I think that the best approach is here, trust me on this. And if there's something that doesn't make sense on the assignment with respect to generics, I don't remember exactly how I described them. I don't think I actually called them generics. But the wording is something like, here, use this piece of code. Just trust me on it. If you have a question on that, feel free to send me email, and I'll give you either an answer that will help you finish the assignment, or if it's not something that's crucial, I'll say I'm going to explain that on next Tuesday or something like that. Today is Tuesday, right? Okay. So that's iterators. Now, let's go back to the main part of the chapter. I won't talk about sections 3 and 3.4 because they're kind of case studies. 3.3 is especially an excellent practice. A way to get practice making collection abstract data types. So last class we made a throttle. We made a throttle class. This chapter starts off by saying throttle classes are cool, but they have very limited applicability. Collection classes, we talk about things in a lot of collections. This room has 27 computers in it. This room has approximately that many chairs. They're collections of things. They're not just a single object. An airplane has a throttle. Woo, great. Especially with data structures, the whole point of this course is to talk about collections of things and how we can manage collections of things. Because most problems involve lots and lots of collections of things. So let's dive right in and actually complete this interarray bag thing. So we go back to page 113. So let's talk about what this bag of integers is going to do, going to behave like. It's a bag, and it contains integers. There's no inherent order, there's no structure, it's just, I don't know how else to describe it than it's a bag. You know, you have a bag of blocks. There are just a bunch of blocks in that bag. And you dump them out, and there's no order, there's no structure. It's just a bunch of blocks. Obviously, there's some containment here. So this is a bag of integers represents integers that are in this collection and not integers that are elsewhere. So it's not every integer in the world. It's just this certain specific subset of integers. And I think there's no restriction on whether or not we can have duplicates. So if we add 3 to this bag, we're more than welcome to add 3 again. But we're also more than welcome to add 5, 7, 13. We're going to use an array as the backing, the actual storage method. So this introduces a concept that's pretty much invariant across all data structures. The data structures provide an interface on top of some data storage mechanism that already exists in Java. Our responsibility is to build this thing so that other parts of our program can easily access the data that's stored somehow. We really don't care how it's stored, or the rest of our program doesn't really care how it's stored. We just want to make it easy for the rest of our program to get access to this data in the way that makes sense to it. And it's our responsibility to take whatever we have available to us, arrays, other objects. Later in the semester, we kind of alternate between using objects to be our data storage method and arrays to be our data storage method. Sometimes we have arrays of objects, which will become fun. That's how we'll actually end the class when we talk about trees. But arrays by themselves are very limiting. We have random access to any element. There's no control over what can be stored in that element, what can be retrieved from that element. An array is very simply an ordered list of objects with some static size. If we have an array of size 8, and we want to store 9 elements in it, we need to get ourselves a bigger array. Most of the time, when we're trying to solve a very specific problem, we don't really care how big the array is. We don't want to care how big the array is. We just want to store stuff and then retrieve it and not worry about that. Collection classes and the data structures that we're going to build can have that property. Really, that property is just when we run out of space, we create a new array, copy the contents of the first array into the new array, and then store the new array. And it's completely transparent to anything that's using this data structure. So let's talk about what that's not my enter key. That's my enter key. What this int array bag data structure will need. It needs a constructor. And the book wants it to take an initial capacity. Whoa. There we go. It wants it to have an add method so that we can put things in this bag. It wants it to have an add many method. This should be new syntax that you've never seen before. This is actually how the printf. I've talked about printf in here, right? I know I talked about it in the other class yesterday. I know the author talks about printf at some point in this book. Don't recall where. But Java now has the ability to support methods with an arbitrary number of arguments. The syntax like this must be the last parameter, the last listed parameter. Basically, those three dots say an int and some more ints to some eventually terminating. This list eventually terminates. And we'll see how to use that. We'll see how to both get information from those arguments and use this method briefly, shortly. He also wants, no, not static, public void add all. And what does this method do? Just by looking at the method signature, we can tell a lot about what this method is supposed to do. Or we can make some assumptions. What are some assumptions that we can make? I know the temperature outside is very soporific. I wanted to nap at work today. So this method takes an int array bag and adds everything in that int array bag to the current int array bag. We already have a remove method from the iterator, and it returns void. The books apparently returns Boolean. I'm going to leave that method out and just use the one we already have. That's sufficient. We have a size method. Which does something that should be blindingly obvious. Book also wants to put a count occurrences. Count, can I spell this? Count occurrences. A union method, which is a static method. I'm going to leave off the clone method, just for time's sake. And then the author wants to have 3 methods that deal with size. So we'll have a get capacity that returns an integer, and insure capacity that will make sure that this bag has enough space to fit the minimum capacity elements in it. And another one that trims the bag to a particular size. It appears to the side, removes all the unnecessary elements in the backing array. So our class is, let's see, that's up to line 34, and we haven't really written any code. This brings up the second main point about data structures, and that is, in general, you have a lot of methods that do a lot of different things. And this is the most tedious part, is stubbing out all the methods. If you design your data structure correctly, most of these methods should be accomplished by no more than maybe 5 lines of code. Many of them even just a single line of code. Even the ones we've already done for the iterator. 1 line of code each. That's not abnormal. So let's start by finishing stubbing these things out and implementing the easy ones. We want to use a backing array, so let's have an array of ints. Let's call this storage. Right? Yes. Okay. So this one has to return an int. Let's start by returning storage.size. That'll be wrong eventually, but for now, it's an int. It'll make this compile. Arrays. Length. If you're going to learn languages, I recommend not trying to learn other languages at the same time. This will also return an int. Let's return 0. That's an int. Null is always good to return for things that require an object to be returned. Get capacity. This we can actually give the right answer for. And this should be storage.length. What's next? Okay. Int array bag compiles. Let's create a new one. with a very creative name. Give it an initial size of 20. So now all of this should compile, and because we haven't changed any of the iterator stuff, it'll still print out just 0 through 9. But the important part is that every single one of these methods has been stubbed out. This will compile. That's step number 1 in creating a data structure. Because if it doesn't compile, it can be very difficult to test. No. If it doesn't compile, it is impossible to test. And I definitely recommend testing incrementally. Implement a method, test that method, make sure it works. Add another method. Well, implement another method. Test it, make sure it works. And one way you can use that is build your main program to work exactly the way you would expect this data structure to work. Calling the methods you expect to call, even if those methods haven't been implemented yet. In fact, especially if those methods haven't been implemented yet. Because then, when you go back and implement them, if your output doesn't make any sense, you know that your implementation is not exactly what it should be. This is something that's been formalized into something called test-driven design. Very useful, very helpful. So let's start at the top and go through and implement these methods the way that they should be. But before we do that, let's look at the diagram on page 125. The way we're going to use this array is that, in theory, the array will have more capacity than the elements in the bag are actually taking up. So we need some indication of what the last valid index in this array is. So we have an array of size 20. We're only using 10 of those elements. We should have something that points to index 10 and says, this is the first invalid index. So, because in Java arrays are 0 index, we can use the same value to point to the first empty element in this array and represent the size of the bag. So let's call it size, and it should start out at 0. The first empty element in the array is 0. So for add, we need to do 2 things here. The first thing is make sure that we have space in the bag to put the element. So we should ensure capacity size plus 1. No. Ensure capacity size. Right? We want that index to exist. Hang on. I'm confusing myself. No, I was right the first time. Size plus 1. We want size plus 1 elements in the array. At least that many. The second thing we need to do is store this element, this integer called element, in the array at index size. So storage size plus element. And now we need to increment size, because the first empty index of the array is now the next one. Right? Questions on that method? At this point, I'm going to go down to my iterator stuff. And change some of it so it actually prints out the contents of this bag. So if current is less than size, that's what we want. Here we want to get the element at current. So storage current, increment current, and then return the element we got. And we're still going to leave remove unimplemented. Any questions on that? So now we can go back here, add some things to my my very long named int array bag. Let's add 3. Let's add 3 again. Let's add 5. Let's add 13. What will this print out? Three, 3, 5, 13. Okay. So that works. So now this many items, or add many. It turns out that when you declare a method like that with int ... it gives elements to you as an array of ints. So here again we need to do two things. We need to make sure we have enough space for everything, and we need to copy the values from elements into storage. So Insure Capacity and here a common trick is to make sure a common convention in developing data types is to always make sure that you have at least twice as much room as you actually need. And this is what the book uses in its implementation of the add many. So they have a check to make sure that what is it, size plus elements length is greater than storage length. So that means the elements won't fit. If that's the case, then we will ensure capacity size plus elements length times 2. Now we need to copy the elements from the values from elements into the values in storage. One way to do this is to iterate through all the values and elements and copy them individually into storage. But there's actually a shortcut that the book uses, and this is listed on page 129. There's a method called system.arrayCopy, and it takes 5 arguments. First one is the source array, which in this case is elements. The second argument is the source index, so where to start in the array. We want to start at 0. The third argument is the destination array, which in this case is storage. Storage, not torage. Fourth argument is the source, the index of the destination array, where these elements should start being copied in, which should be size. And the last argument is the number of elements to copy. In this case, it's elements.length. And finally, we need to update size so that it reflects the actual size. Any questions on that? Let's see if it works. Looks like it worked. Let's implement another method. Who wants to pick a method and tell me what I need to do to implement it? I wish I knew all of your names because then it would be much easier to call. So I'm kind of limited to asking for volunteers. And remember, there's remove much further down in the code. Dion, do you want to start us off? I'm sorry? You don't think you could? How about count occurrences? We're counting something. So we might want to keep track of how many occurrences we have, right? And then eventually we'll return that. How are we going to know how many occurrences of this particular target there are? No, that'll tell us how long the bag is. Right. So my bag has 2 3s in it. So how would I determine that? First of all, that 3 is in the bag, and second, that there are two of them. I'm not concerned with efficiency here. We'll deal with searching and sorting are themselves topics later on in the semester. So efficiency, don't even worry about it. So a for loop. What are my conditions for the for loop? That's kind of a trick question. How am I going to construct the part between parentheses for the for loop? So we have that option, or we have that option. You're going to go with the left? Okay. So what am I going to put there? The for loops are, okay, so in most scripting languages, the for loops are more like the variety on the right, but they all have essentially the same pieces. There's some initialization step, some condition, and then some approach. So what's my initialization step here? What variable name do you want to use? Okay. What's my condition? Less than the length of the bag. Okay. I'm going to jump out of here real quick. Since we're using that, I'm not going to return storage.length. I'm actually going to return size. Okay, so what am I going to do in this for loop? Right. Any questions on that? What did I do? Variable count might, yeah, okay. So let's use this method. Int array bag count occurrences of 3. Make it a little more interesting than something else. And let's actually use that on a couple things. Something that I know isn't in the bag, and something that is only in the bag once. So it's not very descriptive, but those first 3 lines are the number of occurrences of 3 in the bag, which is 2, it's in there twice. The number of occurrences of 1 in the bag, it's not in there at all, so it's 0. And the occurrences of 13, which is 1. I'm going to leave some of these methods unimplemented. You can read about their implementations in the book. We're not going to break quite yet. We still have 10 minutes left. But the second half of the class, I recommend going through section 3.3 that talks about the a sequence abstract data type. Doing a lot of the same things. But it's less guided. It presents the problems and you get to solve them. I'll also talk a little bit about the assignment and make sure I've talked about everything that you need to do the assignment. But first, I want to do Insure Capacity. So I've already mentioned kind of how to accomplish this. We have an array that may or may not be the right size. If it is too small, we need to make it bigger. I'm trying to find the book's implementation so I can be as close as possible. There we go. Okay. So the way the book does this is immediately create an array called bigger array, the very descriptive bigger array. Then the rest of the method is only executed under the condition that data.length, we didn't call it data, we call it storage, .length is less than the minimum capacity. So if we have enough storage, we don't do anything. We just say, yes, we have enough storage. But if storage is too small, then we make it bigger. And the way we do that is put into bigger array a new array with this minimum capacity. And then we again use that system.array copy with the source array, the starting index, the destination array, the starting index, and the number of elements, which should be storage dot length. They use size. It really doesn't matter because any item in the array beyond the size index is meaningless. And then we make storage point to this bigger array. And that works because array variables are reference types, just like objects, not like primitive types. So when we say storage equals bigger array, we're not copying the contents of bigger array into storage. We're copying the reference to bigger array into storage. So after line 59 is executed, storage and bigger array both point to the same place. And then once we finish executing this method, bigger array goes away, that reference disappears, and then only storage points to this new array. Questions on that? This is one of those things that if we didn't have abstract data types, we have to do ourselves, and it would be very irritating. If you've ever seen C code, things like this are littered all over the place. So having the Java idea of encapsulation makes this a lot nicer. When we're using an int-array bag, we don't need to worry about how big this bag is. We just know that it's containing everything we've ever put into it and haven't yet removed. Which, speaking of removed, we can't actually remove anything right now. So let's go ahead and that signature doesn't seem right. Huh. So let's go ahead and actually implement that method the way the author had it. So boolean remove right. Yes. He calls it target. Target. So we need to do two things here. We need to find the occurrence of this element, assuming it's only in there once, which I think is the assumption that the author makes. Right. And he says he uses a while loop. Right. So this goes through and searches for the target. The condition is while we're still within the size of this array, and this particular index that we're on is not the value of target. If we find target in this bag, we'll jump out of the loop and index will be something less than size. If we go all the way to the end, index will be equal to size. That's how it'll fail the condition of the while loop. Make sense? Yes. So if we're still within the bounds of the array, and the value at this, I have an extra parenthesis in there, but if the value at this place in the array is not the one that we're looking for, we keep going, is basically what it's saying. Otherwise, we stop. And we stop with either one of two conditions. Either index is equal to size, which means we went all the way through the array and didn't find what we were looking for, or index is less than size, which means that we found what we were looking for and we actually want to remove it. So once we have that, I'm actually going to flip the order in which the author checks these conditions, just so that the actual condition is identical. Index less than size, index less than size. The author uses index equal to size to test for the opposite condition. If index is less than size, that means that we found target, right? So the first thing that we need to do, well, there are a couple different ways to do this. And the way the author chose to do this, which is actually a pretty elegant solution to the problem, is take the last element, the final element in this array that we have, the last element that's actually in the bag, move it to the index where target was, which now means that there's an extra invalid element at the end of the array, and the one that was at the end is now in the middle, and then he decrements the size of the bag, as opposed to removing something in the middle and then trying to shift everything to the left. That's kind of inefficient. Since a bag has no order, it doesn't matter what order the bag is in, we can do that. We can take an element from the end, stick it in the middle where we're removing this element, and then change the size. Questions on that? So in order to accomplish that, we'll say storage index equals storage size. But right now, size points to the first invalid element, which is not what we want. We want the element at the end. So one way we could accomplish this is do that, but we still have to decrement size by 1 anyway. So we might as well do that first. And the final thing, we have to return true. In the opposite case, which we really don't need an else because if the if executes, we return. So if we don't get to these statements, the if happened. If we do get to these statements, that means the if didn't happen. We can simply return false. This was not in the array, or in the back. Any questions? Let's remove 5. What's going on? Did I spell something wrong? Ah. Something like that. There we go. Yes, I know. So I add 3, I add 3 again, I add 5, I add 13, I add 12, 4, and 8. Then I remove 5, which means that 8 should go after the 2 3s, and then I should have 13, 12, 4. Is that what I have? 3, 3, 8, 13, 12, 4. Yep. Okay. Any questions? We'll break for 10 minutes, and then when we reconvene, you can work on the... No, when we reconvene, I'll talk about the programming assignment. Let's see, hang on. Programming assignment 1 was assigned last Thursday and is due next Thursday. Or this Thursday, rather. Programming assignment 2 is out this Thursday and due the next time. I'll talk about programming assignment 1. If I haven't already. Hang on. I'll figure out what programming assignment I'm going to talk about, if I'm going to talk about any, in the next 10 minutes. And when we reconvene, you can work on practicing building collection classes. How about that? That's the one thing I'm sure of. All right.